Hi students, this video is a quick demonstration about Lab 1 of Digital Electronics module ET0901. Okay, you're watching this video probably because you face some challenges of running through the lab or you don't understand certain procedures or the code in the lab. Okay, so let me walk you through this real quick. Okay, I may not be able to cover every step, but I'll try to cover as much as I can. Okay, so first of all, you need to open this Vivado software, version 2019.2. okay, quite latest version. All right, I think after you have installed the software, it should be appear on your desktop, so just double click on that and boom, you're here. All right, so you can start by creating a project by clicking here. Okay, creating project. All right, and click on next. Okay, then you need to change your project location. I've already changed mine. Okay, so you can basically create a folder similar to this. All right, if it's convenient, D drive, ET0901 lab/lab1. okay, because this is the first lab. All right, then you should give your project name to be Lab1. okay, then you can click next. Okay, but you know, I'm facing this problem because I already have my Lab1 in my folder, so I can't use the same name. So let me just call it Lab1 demo. Okay, Lab1 demo. All right, click next. All right, choose RTL project. Now I need to add sources, right? So make sure the target language is Verilog. Simulator language is also Verilog. Okay, now we can add files. All right, go to this folder, D drive ET0901 lab and lab1 folder. I believe you have already downloaded the source files and put in the respective folder. Okay, so go to this folder. All right, copy this file bcd to decimal.v. all right, click OK. This is our source Verilog file. Okay, click next, and now we need to add constraint file. I mean, although this is optional, which you can add it later, but we choose to add now, so we save some trouble later. So add files, then choose the XDC file. Okay, this is a constraint file extension. Okay, XDC Xilinx constraint file. Okay, bcd to decimal.xdc. Click OK. All right, make sure this copy constraint file into project is checked. Okay, I think similarly we have to make sure this copy sources into project is checked. Okay, so we have to make sure that. I think by default it is the case. All right, but if it is not, please check the box. Okay, click next. Now we need to choose which FPGA chip we are targeting on. Okay, we're using this Basis 3 board, so you know we have to choose the FPGA. Actually, in Xilinx there are a lot of FPGAs they're producing, so we have to choose the FPGA chip. Search for XC7A35 TCPG236-1. okay, this FPGA chip. Okay, you can see that it has 236 I/O pins, I/O buffers 106, lookup tables 20,000 over. Okay, 40,000 flip-flops and 50 block RAMs. Okay, so this is the FPGA target we're using. Okay, so click next. All right, so this is the summary page. New RTL project, one source file, one constraint file. We chose our target device, which is RTX 7 series FPGA. Okay, speed grade is -1, which is the lowest. Okay, so this is really the commercial grade. Okay, if you are using military grade or industrial grade, then you should use -2. If you're using even higher grade like military grade or space grade, then you might want to choose -3. Okay, that would be the highest grade. Okay, anyway, click finish. All right, then the software will initialize and create a project for you. Okay, so firstly, you go to you gotta wait for a while. Okay, wait for the source file to appear. You can double click on the source. You can see the Verilog file is there. Okay, there's a module. Okay, I mean, when you are doing this lab, you may not understand this code by now, because probably that's part 3 of chapter 2. Okay, it's okay if you don't understand. This lab is especially for you to understand the flow of the FPGA design. Okay, right. So we can also open the constraint. Okay, we can also open the constraint. All right. Right now, everything is commented. You see these, you know, the hash command key, basically command character. Okay, everything is commented. All right, everything is commented. Okay. In here in the source file, the ports we're using switch 3 down to 0 and LED 9 down to 0. Okay, so we have to uncomment these input and output ports in the constraint file. So we have to go for switches. Okay, switch SW0 to SW3, right? So we gotta uncomment this. All right, you can just basically select all these lines from SW0 to SW3, and this is the magic button. Click on uncomment. All right, then they will be uncommented. All right, so switches are uncommented, and we need to uncomment the LEDs. Okay, so the LED we need to uncomment from 0 all the way to 9. Okay, so we need to do that. Okay, so now we have 10 LEDs, you know, available, 9 down to 0 or 0 to 9, either way. All right, 4 switches available. Okay, these are essentially the push up and down switches, two-way switch. Okay, after that is done, you see there's a, you know, a star mark there, meaning that you have already modified. Now you need to save it. Okay, just click on save. All right, so we're good. Okay, all right, so we can actually create a block design. No, not block design. We can open elaborated design here. Sorry. Okay, just click OK. It'll take a while for the elaborated design to be ready. Basically, this tells us, you know, what we are coding for. Okay, in terms of our Verilog code. Okay, so let's just wait for a while. Okay, so essentially this is you know, your module symbol. Okay, you have created a module. You have 4 inputs. All right, and 10 outputs. All right. Okay, so that's essentially your block diagram. Okay, I don't think by now you have any details down there. Okay, nothing is there, although it shows schematic, but it just gives you a simple symbol. Okay, so now we can actually add some we can run our simulation, but before we can run simulation, we need to add simulation code. So we go to this source pane. All right, open up this arrow. Okay, now we don't have any simulation files. We don't have any task bench. Okay, so what we need to do is we need to add source. Okay, we need to add source. All right, and we need to add or create simulation sources. Okay, make sure we select create simulation sources. Click next, then click on add files. All right, so here the test bench file, bcd to decimal underscore tb. TB stands for test bench. Okay, we gotta select this and click OK. All right, make sure copy sources into project is checked. Okay, click finish. Now wait for the simulation file to be loaded. Here it is. Okay, this is our simulation file. Okay, it basically specifies the input patterns for us to test our module. Okay, so basically you can see that the module BCD to decimal underscore decoder is under the test bench, and it is under the name called DUT, device under test. Okay, I think we can open up this. Let me try to. Yeah, we can. All right, so you can see there's a BCD to decoder test bench, and in this test bench it basically changes the switch input, and by changing the switch input, the output will also change. So we will be monitoring all the outputs. Okay, so let's see how it works. Yeah, so you can see actually the switch changing pattern is from 0000 to 1111. So it's kind of a binary increment. Okay, from 0 all the way to 15, and then we end the simulation. Okay, and basically the value changes every 10 time unit, and the time unit I believe is time unit is 1 nanosecond. So every 10 nanosecond we change the value once. Okay, so that's essentially how it works. All right, now let's try to run the simulation. Okay, you go to simulation. All right, you can right click and click on simulation settings. Okay, you go to simulation tab, and you can change the simulation runtime. So if we look at this test bench, right, so it changes from 0 to 15 every time it delayed by 10 nanoseconds. So essentially we need to arrange for about 16 of 10 nanoseconds. So essentially 160 nanoseconds. So let's just put 160 here. Okay, 160. Okay, then we can click OK. All right, so I think we're set, and we just click on run simulation here, run behavioral simulation. Okay, and wait for the simulation window to pop up. Okay, so in the meantime, you should be familiarized with all these panels and interfaces. Okay, to understand the software a little bit more. Okay, I think now the simulation window is up. Okay, so you can see that there's your input, there's your output. Okay, but here you don't seem to see the input changes. Okay, that's because you haven't zoomed to max. Okay, so you're gonna click on this zoom fit icon. Okay, now you can see the value changes from 0, 1, 2, 3, 4 all the way to F. F stands for 15. All right, so if you can even open up the switch, all right, you can see switch 0, 1, 2, 3, how they change its value from 0, 0, 0, 0 to 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Okay, that's what you have learned in DE. All right, so yeah. And you can now open up the LED. All right, so you can see actually the LED is showing which LED is enabled. Okay, remember how the decoder works. Essentially, you give a binary code, then one output will be activated. That's how decoder works, right? So at 0, 0, 0, 0, then your output 0 will be activated. That's your LED 0. Okay, LED 0 will be activated. Okay, you can actually add a marker there, or cursor, whatever you call it. Okay, and if your input now is 0001 now, okay, or your input is 1 here, okay, your LED 1 is up, and the rest of your output are all 0 or deactivated. Only LED 1 is activated, and so on and so forth until your LED 9 is up. Okay, but after your input reaches 9, when it goes to A, B, C, D, E, F, nothing is activated for the output here. You see all the output are zeros, all the output are zeros here. See 0 0 0 0 0 0 0 here, which means that anything that is beyond 9, okay, will not activate the decoder. So that's why it's called a binary to BCD, right? Sorry, it's a BCD code to a binary or decimal value, okay, to a decimal value. It doesn't go to hex, all right? It doesn't go to hex. So the rest, you have no activated signal here. All right, so that's essentially how you run the simulation. By doing this, you verify that, oh, the code works, okay, when you design something. You can change the radix, okay, of the signals, okay, where it's the radix, okay, here. So now it is default, I believe it is hexadecimal. You can also change it to binary. So you can see it changes to binary now. Okay, 1111, that's F, 0000, that's 0. Okay, so you can also change it to hexadecimal. Okay, that's essentially what we saw before. Okay, LED we can also change. Okay, let's see whether we have decimal. Okay, we can change it to unsigned decimal. Okay, you can see it changes to decimal value. Okay, it changes to decimal value. Okay, 1, 2, 4, 8, 16, basically power of 2 values. Okay, all right. Okay, so that's essentially the simulation. Okay, after we are happy with the simulation, we can close it. Okay, so we can just click on File, Close Simulation, click OK, and you don't need to save the waveform, so just discard it. Okay, so let's wait for the simulation to be closed. Okay, after that we can run synthesis. Okay, or we can just click on synthesis. All right, you can choose number of jobs to run this synthesis. Okay, essentially number of cores that you need to you want your CPU to be occupied. Okay, I mean, if you want it to be done faster, then you choose more jobs. Okay, if you have other things to be running parallelly, other software, then you may want to choose maybe 4 or even less. Okay, I'm just going to choose 8 just to save us our time. Sorry, click on this, click OK. Okay, so the synthesis is a process to convert your code, all these code. Oh, I can't click right now. Okay, now it is happening in the background. So essentially the synthesis, okay, right now it is running. You can see it is running. Okay, it is trying to convert your Verilog code into the actual gates, okay, so it will probably take 1 to 3 minutes. So let's wait out. Once it's completed, it will pop up some windows. So you gotta be a bit patient. Okay, you can see here it is running. Okay, so something is running, so you better not change the code at this moment. Okay, so yeah, let's just take a break. All right, until it is ready. Okay, so it's ready. Okay, synthesis successfully completed. You can choose to open synthesized design. Okay, yeah, so we just say yes, close the elaborated design and open the synthesized design. All right, so basically it show you, okay, essentially that's where your logic is, if I'm not wrong, or may not be, but anyway, what you can do here is you can open the schematic Okay, just click on the schematic here. Oh, sorry, did I click on the wrong schematic? Okay, hold on. Okay, hold on. Click on the schematic. All right, so here you can see, okay, there's some gates. All right, you may not understand all the gates, but you know, these are essentially buffers. These are lookup tables, which, you know, does certain things inside it. Sometimes you can click into it, or sometimes it's just kind of a basic block in FPGA, so you cannot see what is inside. Okay, but essentially these are some basic blocks in the FPGA that you can just grab and use. Okay, then there are some output buffers go to your pins. Okay, go to your pins. All right, so this is essentially synthesis. You have already generated the net list. What you can do now is you run implementation. Okay, so here run implementation. Again, I use 8 cores. Okay, implementation is the process that converts your schematic netlist into the real layout in the chip. Okay, so it does the placement where your circuit will be placed in on the FPGA. Okay, is it on the top left corner or the bottom right corner? Okay, and it also does the routing, okay, to optimize your design to try to reduce the delay. Okay, this process will also take a few minutes depending on how large your system is. Sometimes when your system gets larger and larger, it can take even hours. Okay, it can even take hours. So let's wait for a while before it is completed. Okay, again, once it's completed, you will see a pop-up window. Okay, you will see a pop-up window. So you can also click on the design runs and see what is going on here. Okay, you can see that implementation is going on. It is running route design, or it is doing the routing job. Okay, so finally it is done. All right, you can choose to open implemented design. I'm just gonna show you. So before that, we need to close the synthesized design. All right. So wait for it to open. Okay. By the way, you can actually open up this project summary and see how much resources you have utilized. Okay, this is the utilization. All right, it shows that you only use 1% of the lookup table, and you're using 13% of the I/O ports. Okay, this is a graph and table. You can also show you only use 5 lookup tables. There are over 20,000 lookup tables. You're only using probably about 2%. And I/O you're using 14 because you're using 4 switches and 10 LEDs. There are 106 available I/O ports. Okay, so you're using 13%. Okay, they also simulate the junction temperature. It will be 40 degrees C. Definitely you don't want this temperature to go very high, then your FPGA will become very hot. Okay, so again, let's come back to here. So actually here you should be able to see the routing. You can see the nets, the routing here. Okay, So definitely there will be a pin here, but it looks like your circuit is here. Let me just zoom in here. Okay, should be, yeah, so your circuit is actually here. Okay, it's actually quite small there. All right, but you can see your circuit. All right, and all the connections. Okay, so essentially that's this is a output buffer, O buff. That's a output buffer. Okay, and these are all the all the nets. Okay, all the nets. Okay, so yeah, so this is a very simple design. So you can see it occupies only a very small area. Okay, right. So after the implementation, you can generate bit stream. All right, the bit stream is something you need to generate to program onto the FPGA. So this is not as straightforward as microcontroller programming. You probably just need to generate a hex file and then you can just program it directly. But for FPGAs, we need a few procedures for the bit stream to be generated. Okay, so bit stream is essentially a binary file. Okay, it's just a binary file similar to the hex file, which can be programmed onto the chip. Okay, which can be programmed onto the chip. Again, the write stream process will take probably about 1 to 2 minutes. It shouldn't take very long. You just have to wait out before it's completed. So in general, I would say your entire FPGA procedure will take at least about 15 to 20 minutes. Okay, before you can get a bit stream to load onto your chip. Okay, so let's just wait out for a little longer. Okay, you can also see the reports here. Okay, full report are generated. You can see the report to see the timing performance, the power performance. So here is the power performance. Okay, essentially signal will only cost about 0.037 watts. Logic is 0.025 watts. Okay, these are all simulated values, but company like Xilinx, they have been doing this for very long, so the estimation is pretty much accurate. Okay, so a lot of power is kind of consumed on the dynamic part. All right, okay, all right, so good. Bitstream is successfully completed. All right, we don't have to view reports this time. Okay, you can open Hardware Manager immediately, but if your computer is not connected to a Basis 3 board, basically you cannot detect anything. So you need to connect your hardware board to your computer at this stage before you can open a Hardware Manager to program to it. Okay, so I've already connected the board here, so just click OK. All right. Now Hardware Manager says, my device is unconnected, so I need to connect my device. Just click on Open Target, Auto Connect. So you just click on Auto Connect, it will just connect the whatever device that is connected onto your computer. So just search for it. Okay. If it is connected, then it should be able to detect. Okay. So I think, hold on, is it connected or not connected? Yeah, I think it is connected. So you can see this guy, this is the FPGA device XC7835. All right, it is already programmed because I already programmed another code onto it, so it's already programmed. But it's okay. You can override the program. You can override the program unlimited times. Okay, that's the good part for FPGA as well. So you can, it is fully programmable, it is reconfigurable. Okay, so if you want to program, just click on program device. All right, if you are in the project, it will directly load the bitstream generated just now. Okay, but if you don't trust it, you can click this dot 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 and see whether this bitstream .bit file is generated just recently. See, this is generated just today. Okay, I'm doing it in the evening, by the way. All right, so yeah, so you can just click OK. All right, and you can just click on program. Okay, so once you click on the program, it will start to program onto the chip. All right, the programming takes very short time. Okay, so after that is done, your board should be working by now. Okay, but now I cannot show you my board because this is really a kind of a screen capture. I can't put the board into the screen, so it's unfortunate, but this is essentially the whole FPGA design flow process. Okay, so I think by watching this video, you can get your Lab1 done pretty smoothly. If you cannot program onto the chip, if you're doing it at home, at least you can reach the bitstream generation step. Okay, so I think that's it. I hope you had fun. Okay, I'll see you next time.